Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Intermolecular Potential and Equations of States. So, we will be discussing a few equations of state. In those equations of state, how the intermolecular potential is playing role, that is what we are going to see. Because for real gases we know that the intermolecular potentials are important, and then what are those intermolecular potentials we have already seen in a couple of previous lectures, right. So, now we try to make use of those intermolecular potential in describing these equations of state or delineating the existing equations of state. That is what we are going to see in this and then coming couple of lectures. There are hundreds of equations of states are available, even more, but we cannot go through in details of all of them. So, what we will be doing, we will be taking the basic very first one, van der Waals equation of state, and then we take a few equations of state which are having similar form except the change in attractive force term. Those kind of those equations of state we will be discussing. Then we will be discussing virial equation of state. Virial equation of state is one such equation of state where the parameters or constants associated with that equation of state are directly related to intermolecular potentials. How are they related to intermolecular potentials and all those things we are going to see. Okay. Now, why do we need information about the equations of state? Because if we know the equations of state, so whether the equation of state is given in a kind of pressure explicit form or volume explicit form, then whether it is for pure gas or for a mixture of gases, then we can know the fugacity of that particular fugacity of a particular component of a mixture or the fugacity of a pure component, provided in which form these equations of state. So, those corresponding equations, generalized equations for the fugacity, when the equation of state is available as a pressure explicit form or volume explicit form, those things we have already derived. So, but now we need to have the information of equation of state, then only those equations are useful, right. So, now that is the important of equation of state. If you have the equation of state, then we can obtain those fugacity information either for a component, any component of the mixture, or for a pure component I, right. So, what those equations, that fugacity equations that we have already derived, that we just have a kind of recapitulation before going into the details of role of intermolecular potentials in equations of state, which are valid for real gases. If the equation of state is available in volume explicit form, then for the fugacity of component I in a mixture, then you can use this expression, right. This expression we have already derived here, only that from the equation of state, whatever the information is there, that information you write in volume explicit form, then you obtain this V I bar, that is dou V by dou N I at constant T P N J. If you have a pure component, then the fugacity of that pure component you can find out using this expression, where you just need to have a kind of a molar volume of that particular component, because for pure component, molar volume is equals to the partial molar volume, or partial molar volume and molar volume are equal to each other. If the equation of state is available in pressure explicit form, then if you wanted to find out the fugacity of component I of a mixture, then you can use this expression. Here, whatever the equation of state available in pressure explicit form, that you do dou P by dou N I and then substitute here and then do the simplification to get the required fugacity of component I in the mixture. And then if you have a pure component, then you can use this equation, right. Here whatever the equation of state in pressure explicit form is there, so that P information you substitute here and then simplify the equation. But the mixtures in general, the major concern is the mixing rules, because all these equations of state are having some parameters or constants which are nothing but a kind of curve fitting parameters kind of things, right. So, those parameters are available only for pure components, they are not available for a mixture of gases. So, that is the reason we have to use mixing rules if you wanted to obtain those constants for mixtures, and there is no guarantee about which mixture rule has to be used. There is no clear cut information that which mixing rule has to be used and all that, and then sometimes mixing rules may not give a constant which relate the or which provide a kind of physical significance about the mixture of those gases. So, that is another disadvantage. right. So, however, we are going to see some of the equations of state where we can even need not to worry about such kind of mixing rules, that is by using virial equation of state etcetera, those things we are going to see now. So, coming to the equations of state, so we start with van der Waals equation of state which consider the intermolecular interactions. Okay. So, we start with that one. So, this van der Waals equation of states, how we can start describing it, probably we can see it as a kind of modification to the ideal gas behavior. Ideal gas behavior, what we have a container, in that we, let us take, if you take a gas, then if you take ideal gas in a container, so the entire volume is available for occupying, because we know this the major assumption of ideal gas behavior is that molecules of the gas does not occupy any volume, or they are infinitesimally small that their volume can be negligible. So, whatever the volume of a container is there, that entire thing is available in general. But in real gases, what happens, you have the molecules of certain size, right. If you take 1 mole of gas and then fill it in a container, so that 1 mole of gas, maybe molecules, whatever the number of molecules are present in that 1 mole of gas, they will be occupying certain volume. So, the entire volume is not available for the occupying. So, whatever the unoccupied volume is there, that may be used as a kind of correction for this volume. Then other thing about the ideal gas behavior is that these molecules, whichever the infinitesimally small molecules are occupying negligible volume, these molecules, they are not interacting with each other. Whatever the interaction is there, that is only because of the collision with the walls and then coming hitting and those kind of things. So, are only possible. Between the molecules, there are no kind of interactions. That is what ideal gas behavior says, or that is the another important assumption. But what we have in reality, for real gases, when the molecules come close to each other, if they come very much close to each other or touching to each other, there may be a kind of repulsion force, and then as they move away after certain distance, collision diameter that we call, then after that, if you further increase the distance between the molecules, then there may be attraction force. As we move further apart, gradually the attraction force increases to certain distance, and after that, if you further increase the distance between two molecules, the attraction force further decreases, and then when these molecules are sufficiently away from each other, the interaction force almost become negligible. Those kind of intermolecular interactions that we have seen. So, now the second point is that this interaction, how can we bring is that molecules are repelling each other when they are touching each other, or if they are certain distance apart from each other, there is a attraction force. How to bring in the concept of attraction force in this ideal gas behavior, that is PV is equals to RT. Now, the ideal gas behavior, whatever the PV is equals to RT is there. So, this molar volume here we can make some adjustment for unoccupied volume, or whatever the real volume that is available for occupying, right. So, that will give the take over the one assumption that the molecules are having negligible volume for the ideal gas, right. Negligible volume, this assumption that can be overcome, if you that can be overcome by replacing this V with certain kind of adjustment or correction factor. Then whatever the attractive forces or intermolecular potential, attractive or repulsive, whatever the forces are there, we have seen these forces are majorly affected by the pressure. If you increase the pressure, what happens? Molecules will come closer and closer to each other, and then more interactions are possible, right. So, then these interactions, whatever is there, ideal gas, no interactions, this can be corrected if you make some kind of a correction with this pressure. Okay. So, this is what is the basis to develop or start with this making start with some kind of adjustment correction to overcome these assumptions that are available, that are existing in the ideal gas behavior. Two important assumptions in ideal gas behavior is that the molecules of gas occupy no volume or negligible volume, right. So, that correction you can take you can make in V molar volume term of this PV is equals to RT, and then in ideal gases there are no interactions, but interactions are stronger especially when pressure increases gradually. So, you if you can make some correction in this pressure term to account for the interactions, then we can have some kind of a priori information or first order information or first order approximation about the real gas behavior. So, that is how this equations of state van der Waals equation of state have been started developing, right. So, those details we see now. So, knowledge of intermolecular interactions can be used to modify the ideal gas model, that is for the cases when the potential interaction between species are important for a given real gas. Okay. So, whatever the intermolecular interactions between the species are there in the case of real gases, if you incorporate in that information in ideal gas model PV is equals to RT. So, then you can make adjustment of or incorporation of intermolecular interactions, and then you can have a kind of model for real gases. So, for this purpose what we do, we will be considering a Sutherland potential that we have already discussed. If you remember in one of the previous lectures, Sutherland potential we have seen this gamma versus gamma is intermolecular potential, capital gamma is intermolecular potential is y axis, and then r axis and then x axis is the intermolecular separation distance. So, this we know it is a kind of having this kind of form, right. So, where this is known as the sigma collision diameter, right. So, this is the diameter. So, when the molecules are coming to the distance closer to this one or smaller, they will immediately be repelling with infinite repulsion forces, but moment this distance between the molecules start exceeding this collision diameter sigma, then what happens, the attraction forces would be there, and then these attraction forces gradually decreases with increasing the this intermolecular separation distance. So, this is what Sutherland potential. Actually, it is a combination of Hart-Spear model and then inclusion of the van der Waals attraction forces. Okay. So, the attraction force part or the intermolecular attraction whatever is there, that is having this form, and then that can be represented by some constant minus k by r power 6. This is what we have already seen. So, this model is a combination of Hart-Spear model accounting for repulsive forces, that is moment they touch each other or the moment the distance between these two becomes equals to sigma. Sigma is nothing but the size of the Hart-Spear that we have, which is also known as the collision diameter in this case. When they touch each other, that is when they are sigma distance from each other. So, immediately they repel, and then repel is repelling force repulsive force is very high. And then van der Waals interactions that describe the attractive forces as I mentioned just now. This development leads to the van der Waals equation of state. So, for this purpose first consider size of molecules on the basis of Hart-Spear model, and then entire volume of system will no longer be available to the molecules, unlike in the case of ideal gas. In the case of ideal gas, whatever the gas you keep on giving, so the entire volume of the container is available, because these molecules of the gas whatever the ideal gas is there, they have the negligible or 0 volume. Okay. So, but in the case of real gases that is not true, it is not possible to have a entire volume of the system for occupying. Okay. So, now one can be accounting for this effect by replacing the volume term in the ideal gas model with one for the available volume. So, that is what we first see, and then we see the other part. According to Hart-Spear model, molecules have a diameter of sigma, that is you have 2 spheres like this, Hart-Spears. So, each one having the diameter of sigma like this. So, that means when they come close to each other or when they are touching each other, the center to center distance is again sigma, right. All the molecules are of same size and then shape. So, then this sigma is also known as the collision diameter. So, that is moment they touch each other, they immediately repel. That means the center of one molecule cannot approach another molecule closer than a distance of sigma because of this reason, because these molecules are considered as a kind of Hart-Spear, non-interpenetrating spherical molecules, that is Hart-Spherical molecules. Now, excluded volume of 2 molecules is obviously 4 by 3 pi sigma cube, right. So, this is the volume that is occupied by 2 molecules, right. So, now you have to divide it by 2, then you will be getting the volume of the molecules, volume of one molecule that is occupying in the system, right. Then whatever that after dividing by 2, whatever the final number is there, that is 2 by 3 pi sigma cube, if you multiply it by Na, that is Avogadro's number, then you will be getting the volume that 1 mole of molecules that are present in the gas occupying. Okay, that much volume, the molecules of 1 mole gas would be occupying, and that is nothing but this 2 by 3 pi sigma cube Na. Now, let us call it as B. B is nothing but the volume that 1 mole of molecule should be occupying, right. So, that is small b. So, we are this PV is equals to RT etcetera, we have taken PV is equals to RT expression that we have taken in terms of molar volume. So, that is the reason here B also we are taking in terms of moles. Otherwise, if you take a number of molecules kind of thing, then this B should be multiplied by the number of moles N. So, we are taking molar basis, so we are not having any B multiplied by N etcetera, those kind of thing are not there. If you are taking B, if you are taking ideal gas like P capital V is equals to N RT form, then this should be B should be multiplied by N. But we are taking this form P small v, that is molar volume is equals to RT. So, here in this case if you use this form, so then that volume whatever that should be subtracted from the available volume is B, not the Bn. Okay. This is the small difference. Okay. Now, to correct for size, one can modify ideal gas model to include only unoccupied molar volume, that is V minus B. Okay. So, whatever now P is equals to RT by V is there, now it should be P is equals to RT by V minus B, because now we are making this correction for the whatever the unoccupied molar volume available for the ideal gas to occupy. So, then under such conditions, since one molecule cannot occupy the space in which the another molecule already sits, then we have P is equals to RT by V minus B. So, now the two terms out of this P V is equals to RT, T is anyway constant for a constant temperature system we are doing, R is anyway constant. Now, for the out of this P and V, we have to make adjustment according to the case of the real gas. For the real gas, the size of the molecules is not negligible. So, whatever that correction is there, that we have already made in V. So, that is P multiplied by V minus B is equals to RT. Now, next what we do? Attractive forces, the intermolecular interactions are negligible in ideal gas, but in real gas they are existing. So, what are those interactions that we have to list out and then write in mathematical form and then make a correction to the pressure, because whatever these intermolecular interactions are there, they are there because of the pressure, okay, or the pressure is the one that is most affecting the intermolecular potential, that we already understood from previous lectures. Because as the pressure increases, molecules come closer and closer to each other, and then intermolecular potential or intermolecular interactions will obviously increase with the increasing pressure. That is the reason interaction terms whatever are there, they should be made a kind of correction to the pressure in this PV is equals to RT. So, one is done. So, now we will be doing the other one. Now, accounting for attractive forces, in the absence of net electric charge, the attractive forces in the gas phase can include dispersion force, dipole-dipole interactions, induction force etcetera. These things we have already seen. We have seen that these are a kind of attractive forces, and we have already seen from the intermolecular potential lecture that all these interactions are related to the separation distance as inversely proportional to r power 6. That is, whatever the intermolecular attraction forces because of the dispersion, dipole-dipole interactions and inductions are there, that we have already seen they are inversely proportional to r power 6. But in equations of state, we cannot have a kind of separation distance as a kind of parameter, right, because separation distance changes from molecule to molecule and system to system depending on the temperature, pressure and all that. So, we cannot have that one as a kind of parameter. But what we can have a kind of volume as a kind of parameter in equation of state. And then what we understand volume is related to the distance as volume is proportional to distance power 3 or cube of the distance whatever is there. So, taking that consideration, volume is proportional to the cube of the distance, then we can say that whatever the attractive forces are there, they are inversely proportional to the V square. Okay. So, hence one can realize that attractive forces are proportional to 1 by V square. That means, we can have some constant, right. So, this is nothing but whatever k by r power 6 term is there in van der Waals attractive force or Sutherland potential, that we are writing some constant let us say A divided by V square. This is what we are writing them. Okay. Now, these are attractive forces, so there are the minus kind of things are this or this is the force that has to be subtracted from the pressure that is there in the ideal gas. Okay. So, that means whatever the ideal gas now after incorporating this size of the molecules, then we have this P is equals to R T by V minus B. Now, there is attractive forces A by V square, that this A by V square has to be subtracted from the pressure. So, then this minus A by V square is coming. So, this is nothing but van der Waals equations of state. So, but how to incorporate this in equation of state? So, that is through the understanding of intermolecular potential topics, we already realized that the variable that most related to the intermolecular potential is the pressure, because as pressure increases molecules come closer to each other, and then when they come closer to each other, then only the interaction should be significant. Okay. So, that is the reason this thing whatever this intermolecular potential or intermolecular attractive force is there, that should be related to the pressure. Thus, correct pressure by including a term that accounts for the attractive forces, and then attractive forces decrease with the pressure. Why should we subtract this whatever the attractive forces A by V square or k by r power 6, why should we subtract them from the pressure? Because as the pressure increases, these forces decreases, attractive forces decrease with the pressure. So, that is the reason subtract a correction term for pressure as follows. So, that is P is equals to R T by V minus B is already there by incorporating the unoccupied volume or the only unoccupied molar volume in the ideal gas, and now we are subtracting the attractive forces from this pressure, right. After incorporating the repulsive forces or by incorporating these molecular size, molar size of the molecules in the ideal gas behavior, then we have this P is equals to R T by V minus B. This is the R T by V minus B is the pressure. Now, this pressure has to be subtracted with the correction that is arising because of attractive forces. That correction is nothing but proportional to 1 by V square. So, we are writing A by V square, some constant A is coming here into the picture. Okay. The same thing we can write in cubic form. If you expand this equation and then you write in cubic form, then we have V cube minus R T by P plus B V square plus A by P V minus A B by P. This is cubic equation of state, because this is called as a cubic equation of state because this is cubic in volume and this is known as van der Waals equation of state. So, the constant A in this equation can be related to molecular constants by integrating Sutherland potential. So, whatever the Sutherland potential that is there, gamma is equals to minus k by r power 6 for r greater than sigma is collision diameter. If you integrate this one, right, at constant temperature, then you can find it out. This one you can obtain this constant as A is equals to 2 pi by 3 Na square k by sigma cube. K is nothing but Boltzmann constant. Na is nothing but Avogadro number. So, we are not going into those details anyway, right. So, further we also realize that this constant A and B can also found by using critical temperature, critical pressure or critical molar volume according to corresponding states theory, right. Whatever the principle of corresponding states theory is there, whatever the principle of corresponding states that we have seen in previous lecture, right. So, then there we have seen the constant A and B of van der Waals equation of state found as a function of a Tc, Pc, Vc. So, we can use them as well. Okay. So, now we realize how these intermolecular potentials are coming into the picture in the equation of states of real gases. So, like that there are hundreds of equations of states are available, but we cannot go into details of all those equations. So, we have started with this simple basic van der Waals equation of state because of one reason, it incorporates or it describes the connection with intermolecular potential in much more simpler and straightforward manner, as we have seen, right. Repulsive forces are connected straightforward, and then attractive forces also straightforward and in simpler manner brought into the model. However, this van der Waals equation we have discussed only because the reason it presented intermolecular potential in much clear way than the others, but it is not accurate compared to more recent cubic equations of state, but it is the simplest one to start with the models or start with the equations of state for real gases. Hundreds of different cubic equations of state exist, and all are approximate equations which fit experimental data. The most rigorous test for an equation of state is near the critical point. The reliability of a given equation of state depends on how accurate it is at critical point, right. If it is more accurate at critical point, then you can say that the equation of state is much more reliable than the others. One equation of state which predicts better at or near critical point is obviously the better one compared to the other ones which do not predict better at critical point. If greater accuracy is required, then a higher order equation of state with more fitting parameters may be used. We have seen this van der Waals equation of state, it is having only two fitting constants A and B, right. So, if you have to if you are expecting a kind of better equation of state, or if you need a better equation of state obviously which is required at high pressures and then high densities etc., then under such condition higher order equation of state with more fitting parameters are found to be reliable. There are a few equation of state with more than 50 parameters as well, but they become mathematically very cumbersome to use in the subsequent calculations to find out the thermodynamic properties. So, now we see equations of state that use the same repulsive term as van der Waals equation of state that we have seen, but different attractive force terms, right, or different attractive interactions terms. So, the first one is the van der Waals equation of state that we have already seen. This constant, as I mentioned from the corresponding states theory, can be found as function of critical temperature, critical pressure or critical molar volume. And then compressibility at critical point is also we have seen in one of the previous lecture. Like that, now you can see this is this part of equation of state, that is RT by V minus B, indicative of the repulsive forces, whereas A by V square is a kind of indicative of the attractive force. Now, we see a few equations of state which are having repulsive force terms same as RT by V minus B, but attractive force slightly different. So, that also we have seen previously in one of the lecture on corresponding states theory, that is Redling-Kwong equation of state. So, here we can see P is equals to RT by V minus B minus A by V plus B square root of T. You can see the repulsive force term here exactly similar form as in the case of van der Waals equation of state, but here you can see the attractive forces are having different form. And then here again these constants we have already found through corresponding states theory, that capital A is given this one, capital B is given this one, and then compressibility at critical point is 1 by 3. This is also we have derived previously, right. So, this is also 2 parameter theory. This is also 2 parameter model, but much accurate compared to the van der Waals equations. Much accuracy in the sense it is much better way reproduces predicts the data at critical or near critical point compared to the van der Waals equation. That is what it mean by it is much better than the other one. For a given system, if you apply both van der Waals and Redlich-Kwong equation, so Redlich-Kwong equation is going to be predicting the experimental data with much better accuracy at or near critical point compared to the van der Waals equation. That is what it mean by better one. Okay. How better way it predicts at critical point or near critical point is going to determine whether the given equation of state is reliable or not. If it is predicting the experimental results much better way at critical point or near critical point, then we can say that those equations of state are much more reliable compared to the others one. The other one is Peng-Robinson equation. Here also you can see the repulsive forces, that is RT by V minus B, exactly same as van der Waals equation of state, but the attractive forces, they are having quite different term, that is A alpha function of T divided by V plus B plus B V minus B, this is what we are having. And then this alpha is function of temperature, and then that temperature, that alpha function is having third parameter as well. So, we can see we can obtain this A in terms of critical conditions like this, and then B like this, and then alpha T is nothing but this one. TR is nothing but the reduced temperature, that is T by Tc, and then this kappa is nothing but it is a function of eccentric factor. Eccentric factor we have seen omega, this omega is known as the eccentric factor, and then we have seen it gives a kind of a prediction how non-spherical a molecule is. Non-spherical in the sense the force field around the molecule is the force field around the molecule, if it is symmetric, then we call them those then we call that molecule as a kind of simple or spherically simple molecule or spherically symmetric molecule, that is what we call. If the force field around the molecule is not symmetric, then we call them non-spherical or complex molecules. For that, how much it is non-spherical, that you can realize through this omega. This is also we have seen in one of the previous lecture. Okay. Eccentric factor, right. So, now we can see this Peng-Robinson equation of state is having three constant, one is the A, another one is the B, another one is the omega. So, obviously, this is going to predict the experimental results much more accurately compared to the Redlich-Kwong or van der Waals equation, right, because if you have more parameters, it is going to it is possible that it is going to predict the data, experimental data much more better way at critical or near critical point. Okay. So, these are a few equations of state that we can discuss, but there are hundreds of equations of states are there. We cannot go into the details of all of those equations of state. Now, what we do? We take a virial equation of state. Okay. As I mentioned, this let us start with the same simple this P is equals to RT by V minus B minus A by V square. V is molar volume, P is the pressure, T is the temperature, B is the parameter relating to the size of the molecules that are size of the molecules of the gas system, whatever we have taken. A represents some kind of proportionality constant of interaction forces or attractive intermolecular potentials. Okay. So, this is what we have seen. Now, this A and B constant, as I already mentioned, can also be found through critical state through critical conditions, that is PC, TC, etc. Those things you can use and then find out, right. But these constant A and B are available for pure systems only, pure gases only they are available, right. But if you have a mixtures or a mixture of gases, then these constants A and B are not available, right. And this A and B for mixtures one has to found from the mixing rules, and then there are many mixing rules. Which one to use for a given system is again a difficult task. That is one thing. So, there is no reliability of this A and B constant for the mixtures, and then for even for the pure components also, these A and B constants are hardly having any physical significance with the system, with the real system. Okay. So, for here B may be relating to the size of the molecules, but not exactly size of the molecules, related to the size of the molecules. Okay. A is what? How it is related to the physical significance, or the physically related to the system. These are the kind of problems that are there for many equations of state. but this virial equation of state is the one which takes into the consideration of the molecular interaction directly while taking this parameters or constants, right. So, what that is indirectly whatever the constants or parameters that are present in the virial equation of state, they are directly related to the intermolecular interactions or intermolecular potentials, and whatever the mixtures, for the mixtures also they are directly related to the intermolecular potentials. The constant, these constant are the parameters of virial equations of state for mixtures also does not depend on the composition, that is the advantage. So, both the things have been taken care by this virial equation of state, but the major problem with this virial equation of state, it is valid, the gives a better approximation for the low to moderate pressure or densities only. It is not suitable for high density systems. So, those things we are going to see now. So, constants or parameters that appear in many empirical equation of state for a pure gas have at best only approximate physical significance, physical significance only, not true physical significance. For mixtures of such gases, usually those constants are obtained by applying composition dependent mixing rules, and it is difficult or many times impossible to justify such mixing rules. Which mixing rule should be used, as there exist many mixing rules. Okay. Further, in order to calculate fugacity in gas mixtures with confidence, it is advantageous to have an equation of state where parameters have physical significance, that is parameters can directly related to the intermolecular forces or intermolecular potential. Okay. So, one such equation of state is nothing but virial equation of state. So, virial equation describes the compressibility factor as a power series in the reciprocal of molar volume, that is Z is equals to PV by RT is equals to 1 plus B by V plus C by V square plus D by V cube and so on. So, series continues, where this coefficient B is known as the second virial coefficient, and coefficient C is known as the third virial coefficient, and coefficient D is known as the fourth virial coefficient, and so on. So, this coefficient B, that is second virial coefficient, it describes the deviation from ideal gas behavior because of the interaction between two molecules, whether it is a pure system or a kind of mixture. Because of the interaction between two molecules, whatever the intermolecular potential is there, because of that one there is a deviation from the ideal behavior. So, that deviation is counted by this second virial coefficient. Likewise, there may be three molecules or interactions as well. Let us say if you have a pure system I, so let us say molecule 1 and molecule 2, right, they may be having interacting amongst themselves, and there may be a kind of a intermolecular interaction, and that is causing a kind of deviation from ideal behavior, bringing in the non-ideality, right. For the same system of I, or the system or gases I, if you take 3 molecules 1, 2, 3, right. So, then these may be interacting like this 1, 2, 3 like this. This may be simplified as 1, 2, 1, 3 and then 2, 3 interactions, that is interaction between these two molecules 1, 2, 1, 3 interaction between these two molecules 1, 3 and interaction between 2, 3. So, this interaction between these 3 molecules again can be simplified as a combination of interaction between two different molecules, that is 1, 2, 1, 3, 2, 3 and all that. So, when the 3 molecules like this molecule 1, molecule 2, molecule 3 are interacting, and because of such interaction if there is a kind of deviation from the ideal behavior, so that deviation is brought into the system or model through this constant C. Okay. B brings in the deviation from the ideal behavior due to the 2 molecule interaction. C brings in the deviation from the ideal behavior due to the 3 molecule interactions, and so on. So, analogously we can take the higher order coefficients. Okay. That is the reason this equation of state is found to be better compared to the other one, because it directly incorporates the intermolecular interactions in the parameters that are existing in this model, that is B, C, D, etc. Right. These coefficients further most importantly depend only on temperature. We are going to see an expression, we are not going to derive, derivations are all part of the physical chemistry, right. We will take the equations and discuss them, right. So, we will be seeing soon these coefficients are functions of only temperature, and most importantly they are independent of the pressure or density. And then further, the unique advantage of virial equation, there is a theoretical relation between virial coefficient and intermolecular potential. So, when we are saying this, this B is between the interaction is because of the interaction between two molecules, and this C is because of the interaction between the three molecules. So, that means there is a intermolecular potential is there. That means these coefficients are directly related to, let us say, gamma 1 2 here, and then here in the case of C probably gamma 1 2 3 molecular interactions. So, those things are directly related to the intermolecular potentials. So, those things are also we are going to see. This is another important, most important advantage of this virial equation of state. Further, virial coefficients depend on composition in an exact and simple manner in the case of gaseous mixture. Let us say we have gas I and J, right. So, then one molecule of Y and then one molecule of J are interacting, then there will be a kind of a second virial coefficient, but that is known as Bij, something like this. Here we can say if it is I, this B is nothing but Bii, same interaction, and this C we can call it as Cii because same molecules. If you have different molecules, then like this it is possible, right. So, that means whatever the interactions, what for the mixtures also these coefficients are directly related to the intermolecular potential in a similar way as they are valid for the pure gases. The equations we are going to see now anyway, right. If you have a same Ij mixture, binary mixture, but two molecules, one I molecule, two J molecules, then it isCijj. Or if you have a kind of two I molecules and one J molecule, then we can have Ciij. So, like this here also this is related to gamma Iij, we can find out what it is and substitute it in the equation to find this one, and then here it is related to the gamma Ijj, and then here it is related to the gamma Ij. So, one can find out this intermolecular potential through the basic concept of intermolecular interaction that we have seen, and then substitute here and then get this virial coefficient. So, that means directly even for the mixtures they are directly related to the intermolecular potential in much more similar way as they are related to the constants of pure system or the coefficients of pure system. So, this virial coefficient is also represented as a kind of compressibility as a function of a power series of pressure, like Z is equals to PV by RT is equals to 1 plus B prime P plus C prime P square plus D prime P cube and so on. So, and these coefficients B prime, C prime, D prime, again they are dependent only on temperature, but not dependent on the pressure or density. That is one of the advantage. But however, this B prime, C prime, D prime for mixtures they depend on composition in a more complicated manner than those appear in equation 1. Equation 1 is nothing but Z is equals to PV by RT is equals to 1 plus B by V plus C by V square and so on. So, this is equation number 1. So, here in this case it is dependent on the composition in much simpler and straightforward manner. But here if you use this form of the equation, this B prime, C prime, D prime are dependent on the composition in more complicated manner compared to the case of equation 1. This is one of the disadvantage, not disadvantage, or you wanted to make a decision which equation should you use, whether the equation 1 or equation 2. One is the straightforward, whether you want in a volume explicit form or pressure explicit form, that should be the one basic criteria. If that is not very important, then you should see the other ones, which way it is better or which way it is simpler for the mixture or which way it is directly related to the intermolecular potential for the mixtures also. Those kind of things we have to see. Further also there are other advantages of equation 1 compared to the equation 2. remember both of them are same, right. One is written in a power series of reciprocal of molar volume, another one is written in a power series of pressure. Okay. However, if you write this in terms of power series of reciprocal of molar volume, it is advantageous compared to writing in power series of pressure, because if the series you truncate after third term, then experimental data can be reproduced by equation number 1 over wide range of densities of pressure than equation number 2. This is an experimental observation for many systems. Further, that virial coefficient B, C, D are evaluated as physically significant parameters by interactions between the molecules, whereas B prime, C prime, D prime, remember we are not calling them virial coefficients, right, we are calling them coefficient, they are temperature only on temperature, but they are not directly related to this intermolecular potential, whereas this B, C, D etc., they are directly related to the intermolecular potential gamma. Okay. This is another advantage. Why should you use this virial equation of state in the form of equation number 1, that is Z is equals to PV by RT is equals to 1 plus B by V plus 1 plus B by V plus C by V square plus D by V cube and so on. And there is a relation between these coefficients of equation 1 and 2 obviously, right. So, you can solve this equation number 1 in equation number 1 you can solve for P by using Z is equals to PV by RT and then substituting that P in equation number 2 simply, then you can get the relation between these coefficients, that is B prime is equals to B by RT and then C prime is equals to C minus B square by RT R square T square, D prime is equals to D minus 3 BC plus 2 B cube divided by R cube T cube. Now, the second and third virial coefficient, that is B and C, can be evaluated from low pressure volume data as B is equals to limit rho tends to 0 dou Z by dou rho at constant T, or and C is equals to limit rho tends to 0 1 by 2 factorial dou square Z by dou rho square at constant temperature, because Z is equals to what we have 1 plus B by V plus C by V square and so on. So, this we can write it as Z is equals to 1 plus B rho plus C rho square and so on. So, let us say if rho tends to 0, then higher terms can be neglected, then we can have what we can do, we can, if you do dou Z by dou rho at constant temperature, we can get 0 plus B when you take only this up to Bth term. So, that means B is equals to limit rho tends to 0, then dou Z by dou rho at constant temperature. Likewise, C also you can get it by limit rho tends to 0 1 by 2 factorial dou square Z by dou rho square at constant temperature. This is how you can get them, right. For many gases, when truncated after third term, that is D term and higher virial coefficient terms are neglected in equation number 1, then it gives good representation of compressibility factor to about 1 of the critical density, that is the advantage, and fair representation to nearly the critical density. As I mentioned, the equation of state, whether it is a reliable better one or not, it depends on how it predicts the experimental data at critical point or near critical point, and we can see at or near critical point, this virial equation of state is giving fair representation of experimental data. These are experimental observation, but to the half of the one half of the critical density, it gives a very good good representation of the compressibility factor that are obtained from experimental data. Okay. So, we can say that this particular equation of state, virial equation of state, is better one compared to the other one, because it gives a fair representation of experimental compressibility factor even at critical densities. Okay. For higher densities, the virial equation is of little practical interest, because experimental as well as theoretical methods are not sufficiently developed to obtain useful quantitative results for fourth and higher virial coefficients. However, this virial coefficient or virial equation of state is applicable to moderate densities, which are in general whatever the vapor liquid or vapor solid equilibrium problems that we have in real life situations. This vapor phase usually it is at moderate densities. So, obviously this virial equation can be made use of, because virial equation is applicable to moderate densities as commonly encountered in many typical vapor liquid and or vapor solid equilibrium problems. Now, as I already mentioned, second virial coefficient takes into the account the deviation from ideal behavior that results from interaction between two molecules. If you have two molecules, molecule 1, 2, then if they are interacting, whatever the interaction is there, gamma 1, 2, this is directly related to B 1, 2. Okay. If it is of same molecule, then we can have B 1, 1 like that or B 2, 2 like that. Third virial coefficient takes into account deviation from ideal behavior that result from the interaction of 3 molecules, let us say 1, 2, 3 molecules if you are having like this. So, interaction between 3 molecules is causing some kind of non-ideality. So, whatever this gamma 1, 2, 3 is there, that can be related to this C, that is third virial coefficient directly. We are going to see those expressions, though we are not going to derive them. Similar way, further physical significance of each higher virial coefficient follows in an analogous manner. From statistical mechanics, one can derive relation between virial coefficients and then intermolecular potential, right. We are going to use them, we are not going to derive them. For simplicity, consider a gas composed of simple spherically symmetric molecules such as methane or argon. Then potential energy between two such molecules, if designated as gamma r, where r is the distance between the two molecules, then the second and third virial coefficients are related to the intermolecular potential gamma r and temperature by these two equations. B is equals to 2 pi Na integral 0 to infinity 1 minus exponential of minus gamma r by kT r square dr. So, whatever the intermolecular potential that you have between two molecules, that if you know that, if you substitute here, you can straightforward find out what is this B. So, now you can see this virial coefficient is directly related to the intermolecular potential through statistical mechanics, right. Similarly, third virial coefficient C is given by this equation, right, where this F12, F13 etc., if you write generalized way, Fij is nothing but exponential of minus gamma ij by kT minus 1, where k is Boltzmann constant and Na is the Avogadro's number. So, it is clear that this virial coefficient or the parameters, they are the constant that they are present in the virial equation of state, they are directly related to these intermolecular potentials, right. So, you can see. So, you find out this intermolecular potential accordingly for the 2 molecular interaction as well as 3 molecular interactions, and then substitute them as a kind of substitute in this equation and integrate them, then you can find out these constants. Okay. So, these 3 molecular interactions also for the same component I, molecule 1, 2, 3 are there. So, these 3 molecular interactions are directly not possible in general in reality. Whatever the interactions are there, they are taken as a kind of combination of interaction between 1, 2, interaction between 1, 3 molecule and then interaction between 1, 2, 3 molecules. So, these interactions, binary interactions again coming into the picture. So, whatever these 3 molecule interaction is there, C 1, 2, 3, it is again related to the gamma 1, 2, gamma 1, 3 and gamma 2, 3. Binary interactions anyway, they are coming into the picture. So, this equation number 8 and 9 applicable to spherically symmetric molecules as mentioned, like something like methane or argon, something like that, right. They are, or the statistical mechanics point of view, they are developed for such simple molecules, but they are having these terms gamma intermolecular potential, right. But these intermolecular potentials, if you have for complex molecules or polar molecules etc., then also they can be used. That is, they are applicable for this B expression, C expression given by equation number 8 and 9, they are applicable for a spherically symmetrical molecule, but they are also valid for essentially stable uncharged neutral molecules, polar and non-polar molecules, including those with complex molecular structure, for which the intermolecular potential depends not only on distance, but not only on distance between molecular centers, a center between the molecules, but also on the spatial geometry of separate molecules and their relative orientation. So, this information should also be included in this gamma. Once you incorporate this additional information about the molecules other than spherical molecules, then when you include those additional information for non-spherical molecules in gamma, so then these equations can also be valid for complex molecules, non-spherical molecules as well. Though these are developed for spherically, symmetrically spherical molecules. Now, coming to the extension to the mixture, most important advantage of virial equation of state for application to phase equilibrium problems lies in its direct extension to mixture, because we have seen even this cross virial coefficient, whatever the B12, C112, C122, these are cross virial coefficient, because they are not of the same molecules, one from the molecule 1, 2 from the molecule 2. 1 from the gas 1, 2 from the gas 2, let us say. Gas 1 and gas 2 are mixed. So, there is a binary mixture B11, B22 are possible, but there is also possible that this B12 as well. This B12 we call it as a kind of a cross virial coefficient. Similarly, if it is about 3 molecular interactions, not only this C11, C222, but also possible C112, C122. These are cross virial coefficient. Because of this reason, we can say that this is the advantage that this they are directly extendable or applicable to the mixtures as well. This extension requires no arbitrary assumption, right. So, there is, if you are using some kind of mixing rules, then you have to make some kind of assumption, etc. But now here there are no such assumptions are involved, because directly we are taking the interaction between different types of molecules in the case of mixture. First, consider the second virial coefficient that takes into account the interaction between two molecules. In a pure gas, chemical identity of each of interacting molecules is always the same, because it is a pure gas, all molecules are same molecules, so their interactions are going to be same. However, in a mixture, various types of two molecular interactions are possible depending on the number of components present. Let us say if you have a binary mixture containing species I and j, there are 3 types of interactions are possible as II, JJ, IJ interactions. I have taken here 1, 2 example kind of thing. If you do the same thing IJ kind of thing, so then BII, BJJ, BIJ are possible. Similarly, 3 molecular interactions if you do, then C triple I, C triple J are anyway possible. In addition to them, cross virial coefficient C I double J and then C double I J, they are also possible, right, for the 3 molecular interactions. If it is 2 molecular interactions, then BII, BJJ and BIJ are possible. For each of these interaction, there is a corresponding second virial coefficient that depends on the intermolecular potential between the molecules under consideration. BII is second virial coefficient of pure I that depends on gamma II, and BJJ is second virial coefficient of pure J that depends on gamma JJ, whereas BIJ is second virial coefficient corresponding to IJ interaction that depends on gamma IJ. This is also known as the cross virial coefficient. If IJ are spherically symmetrical molecules, then Bij is given by same as that of equation number 8. Equation number 8 we have written exactly same without this Ij, subscript Ij here and Ij here. Okay. If I is equals to j, then it is Bii or Bjj. If I is not equals to j, then Bij. So, corresponding, if you wanted to you get Bii, then you have to get gamma ii and then substitute here. If you wanted to get Bjj, you have to get gamma jj and then substitute here. If you wanted to get Bij, then you have to find out gamma ij and substitute here. Remember, this Bii, Bjj are nothing but B for pure I, and then Bjj is nothing but B for pure j, and this Bij is nothing but it is Bij, but not for mixture. It is a cross virial coefficient which is having Bij. Okay. It is taking interactions, you know, for ij interactions, but if you wanted to know for the entire mixture, then we have to have a kind of, you know, different rules that we are going to see. And then all these 3 virial coefficient, whatever Bii, Bjj or Bij are there, they are functions of temperature only, and they are independent of pressure or density, right, and most importantly they are independent of composition. For what composition you need, that is anyway composition will come into the picture, but composition is not making a role in a kind of this measurement of these parameters. Okay. So, Bij is for the is cross coefficient, that is taking an interaction about a interaction between 2 molecules of species I and then species J. Okay. Right. But for the B mixture, this B mixture, if you wanted to find out, this is going to be function of this Bii, Bjj and then Bij plus Yi, Yj. How it is that we are going to see now. Second virial coefficient of a mixture, then you can write it. If it is a binary mixture, then B mixture is Yi square Bii plus 2 Yi Yj Bij plus Yj square Bjj. If you have m number of components, then B mixture is nothing but sigma I is equals to 1 to m, sigma j is equals to 1 to m, Yi, Yj, Bij. Let us say I, j, if you take 1, 2, 3, 4 something like this, here also 1, 2, 3, 4 something like this, with 1, whatever these interactions are there, all should be taken into the consideration, added together with by this formula, and then 2 of I, then all these binary interactions whatever possible, all should be taken into consideration. Then third molecule of I, whatever all these interactions are there, all with 1, 2, 3, 4 and so of j should be taken into consideration. Like this with fourth molecule of I, so all these interactions with whatever this 1, 2, 3, 4 components of J series, like this, they should be taken into the consideration. So, all that if you write in a kind of mix summation form, then we have this expression. If you have only binary mixture, then we have this expression. Okay. This is for the multi-component system, this is for the binary system. Third virial coefficient of a mixture is related to various C, I, J, K coefficient that take into account interactions of 3 molecules I, J and K in a similar manner, and then for the binary mixture containing I and J, but 3 molecular interactions. Remember, binary mixture, but 3 molecular interaction, that is II, triple I or triple J or double Ij or I double J, these kind of interactions. 3 molecular interactions, but for the binary system. Then we can have C mixture is given by this expression. Whereas, if you have m number of components, then C mixture is equals to sigma I is equals to 1 to m, sigma j is equals to 1 to m, sigma k is equals to 1 to m, Yi, Yj, Yk, Cij, This is for the multi-component system having m number of components. Coefficient Cij, is related to the intermolecular potential gamma Ij, gamma Ik and gamma Jk exactly same way as we have seen previously, that is Cij is given by this expression, and then Fij is nothing but exponential of minus gamma ij by kT minus 1, whereas Fik is nothing but exponential of minus gamma ik by kT minus 1, and Fjk is nothing but exponential of minus gamma jk by kT minus 1, k is nothing but Boltzmann constant. And this distance between one I and one j molecule is Rij. Rik is nothing but distance between one I molecule and one k molecule, like this. Okay. Rjk is nothing but distance between one j molecule and one k molecule, like this. So, fourth and higher virial coefficients of gaseous mixtures are related to composition and various potential functions in an analogous manner, as we have done for the 2 and 3 molecular interactions just now, but they are not required. 3 molecular interaction, that equation we got a cubic equation for a binary system like that. Nth virial coefficient of a mixture is a polynomial function of mole fraction of degree n. Then finally, cross virial coefficient, that is Bij, Cij and Cijj can be obtained from regression of corresponding mixture and virial coefficients. Let us say if experimental data is available for several composition, then cross coefficients can be obtained from using this expression limit Yj tends to 0 dou by dou Yj of B mixture is equals to 2 Bij minus Bii. Bii is known, so Bij you can know if you know what is dou by dou j of B mixture. Similarly, limit Yj tends to 0 dou by dou Yj of C mixture at constant temperature is equals to 3 multiplied by Ciij minus Cii. Cii is known for the pure system. So, then this cross virial coefficient Ciij can be known. Similarly, Cijj can also be known. How do you get these equations? It is simple and straightforward. Whatever this equation number 11 and 10 or 11 and 13, equation number 11 and 13, that is for the B mixture and then C mixture for a kind of binary system that we have written. So, in this equation, these equations what you do, you write in Yj terms. You write in Yj terms by taking Yi is equals to 1 minus Yj, because it is a binary mixture. So, this equation would be in Yj forms. Then what you do, you neglect Yj square and then Yj cube terms and then higher terms if at all existing, then you apply limit Yj tends to 0, then you can get this equation straightforward. Okay. These are the few basics of virial equation of state. We have seen the virial equation of state, and then how this virial coefficient or the parameters associated with the virial equation of state are related to the intermolecular potentials, etc. We have seen virial equation of state in 2 different forms we have seen, and then we have seen the relation between those parameters, that is B, B prime, C, C prime, D, D prime, etc. Those things we have seen, right. We have also seen how to find out this virial coefficient from the intermolecular potential or the expression that we have seen. In the next class what we do, we take a few intermolecular potentials, and for those intermolecular potentials we are going to find out these virial coefficients B, C, etc. The references for this lecture are given here. Most of the details that are presented in this lecture are taken from these 2 books, Prosnit et al. And Koretsky. Thank you.